In this video, we will begin exploring the geometric interpretation of the definite integral. So the first portion of this slide here is just to remind you what we introduced in the previous video, that the definite integral is defined in terms of this limit of a Riemann sum, where what we are summing up here is actually the areas of rectangles. And taking the limit as n goes to infinity ensures that we calculate an actual area, not just an approximation. And the big interpretation that we had of the definite integral is that it represents a net difference of enclosed areas. And I think the picture below is the best way to illustrate this. So if in blue we have the function y equals f of x, then the definite integral from a to b of the function f of x dx is the net difference of area enclosed between the function and the x-axis from a to b. That is, we take the area enclosed above the x-axis, a1, and we subtract away from that the area enclosed below the x-axis, a2. So in our first few examples, in this video and the next, we will explore the geometric interpretation, and it will revolve solely around being able to draw a picture of the function and then use geometric formulas. And then in future videos, we're going to explore how we use this limit of a sum and our special sum formulas to evaluate these more analytically. So in terms of areas, let's evaluate the given definite integral. So the definite integral from -3 to 3 of the absolute value function. So the thing that we need to do is sketch the absolute value function and think about what area it enclosed between -3 and 3. Well, graphically, the absolute value function is V-shaped. So for negative inputs, you have the line y equals minus x. For positive inputs, you have the line y equals x. So if you want to think about the enclosed area, you have the area enclosed to the left. Then you have this area enclosed to the right. So it's the area between the curve and the x-axis. And two key points, 3, 3, and -3, 3. So we could add up the area of this first triangle. Think of this as being maybe A1, and add on to that the area of the second triangle, A2. So both of these triangles have a base length of 3 and a height of 3. So area 1 would be 1/2 base times height, plus area 2, 1/2 base times height. So that's 9/2 plus 9/2, which is simply a 9. So from this geometric perspective, we can very conveniently evaluate a definite integral, but note that there is kind of a caveat here. It only works when the enclosed area is a familiar geometric shape. So let's look at another very common example. So the definite integral from -2 to 2 of the square root of 4 minus x squared dx. And once again, to evaluate this, we need to graph this function that we are integrating. So if we think about y equals the square root of 4 minus x squared, we may not recognize this immediately, but let's get rid of the square root. If we square both sides, we would have y squared equals 4 minus x squared, or x squared plus y squared equals 4. So that would be the top half of a circle of radius 2 centered at the origin. And I say the top half because it's only the positive square root. So the curve that we have, y equals the square root of 4 minus x squared. We're going from -2 to 2. So if we would like to evaluate the definite integral from -2 to 2 of this function, that is a fancy way of asking us how much area is enclosed between that curve and the x-axis. And the answer is, well, it's 1/2 of the area enclosed by a circle of radius 2. So 1/2 times pi times 2 squared. Because the area of a circle is pi r squared, and we want exactly 1/2 of it. So this simplifies very nicely to 2 pi.